Welcome to Podcast Learn and Fun. Let's start today's journey of learning about one of those mind-boggling fields out there, quantum mechanics.
Oh, yeah.
How much can we really know about a quantum system?
Yeah.
And what does that even mean?
Right.
Today, we're going to unpack the difference between pure states and mixed states,
Okay.
which, might sound like something out of a philosophy seminar.
Yeah.
But are actually key to understanding how quantum systems behave,
Right.
especially out here in the messy real world.
And you know what's really fascinating?
Yeah.
These concepts, these states, aren't just theoretical. They have huge implications for cutting-edge technology like quantum computers.
Wow.
And even help explain everyday phenomena like why your hot cup of coffee eventually cools down.
Okay.
Yeah.
Let's start with the pure state, the ideal scenario.
Yeah.
Imagine a system where we have complete knowledge of its quantum state. It's like a pristine, perfectly tuned musical instrument ready to play a perfect note.
Mm-hmm.
Every part is in a well-defined state.
That's a great analogy. And to build on that, what's crucial in a pure state is this idea of coherence.
Okay.
All parts of the system are not just in a specific state, but are also working together in perfect harmony, like a synchronized dance. This harmony, this coherence, is what allows for mind-bending quantum phenomena like interference.
Right.
Think about the classic double-slit experiment. A single particle, like an electron, can actually go through two slits at the same time
Wow.
because its wave function, its possible states, are all in sync and can interfere with each other.
But wait, even in this pristine, pure state where we have complete knowledge,
Right.
doesn't the Heisenberg uncertainty principle still throw a wrench in things?
Absolutely. Even in a pure state, there's inherent uncertainty.
Oh, well,
The Heisenberg uncertainty principle isn't about not knowing enough about a particle.
I see.
It's about the fact that certain pairs of properties, like a particle's exact position and momentum, can't both be known with perfect precision at the same time. It's like trying to pinpoint both the exact location and speed of a wave crashing on the shore. You can get one or the other, but not both with complete accuracy.
So it's not about knowing everything,
Yeah,
but rather knowing everything that is possible to know
right.
within the limits of quantum mechanics.
Yeah,
We can predict the probabilities of outcomes with certainty,
exactly.
but certain properties remain inherently fuzzy.
It's important to remember that pure states, with their perfect coherence, are kind of like theoretical ideals. They're rarely found out in the wild.
Oh, interesting.
And this is where mixed states come in.
Yeah.
This is where things get a bit messier, more realistic, and honestly, even more interesting.
Here's where it gets really interesting. So if a pure state is like a perfectly ordered deck of cards,
Okay.
a mixed state is like that deck after it's been thoroughly shuffled.
Right.
We know the possible cards, the possible states,
Yeah.
but not the exact order.
Right.
Our predictions become probabilistic,
Yeah.
and the system as a whole becomes less predictable.
Perfect analogy.
Wow.
That shuffling, that loss of predictability, is a key characteristic of mixed states. It's
Oh.
driven by what physicists call decoherence.
Right.
The more a quantum system interacts with its environment, think stray particles, heat, even light, the more its pure state gets disrupted. And its different possible states start to get mixed up like those shuffled cards.
So in a mixed state, instead of being in one specific well-defined state, the system is in a blend of possibilities.
Yeah.
And we only know the probabilities of each possibility.
Precisely. Think of a qubit, the building block of a quantum computer. Ideally, we want that qubit to stay in a pure state, so we can perform precise calculations. But in reality, it's constantly bombarded by noise from the environment, which causes decoherence, turning it into a mixed state. It's like trying to balance a spinning top on a bumpy surface. Those bumps, that environmental noise, make it wobble and eventually fall over.
So that's why building reliable quantum computers is such a monumental challenge. It's like trying to build a super precise clock in a room full of rambunctious toddlers constantly bumping into it.
Exactly.
Okay.
And that's why scientists are working tirelessly on developing quantum error correction techniques.
Right.
It's a constant battle against decoherence, trying to keep those qubits in a pure state long enough to do useful computations.
Okay. Before we dive deeper into these techniques and the implications of mixed states, can we quickly recap the key differences between these two fundamental states?
Sure. It all comes down to knowledge versus uncertainty, coherence versus decoherence, reversibility versus irreversibility. Pure states represent complete knowledge, perfect synchronization, and predictable, reversible behavior. They're fragile and easily disrupted. Mixed states embody incomplete knowledge, a loss of that synchronized dance due to decoherence, and less predictable, often irreversible behavior.
Wow.
And they're much more common in the real world.
So why does all of this matter beyond the theoretical?
Great question. The distinction between pure and mixed states isn't just an abstract concept. It has real-world consequences. In fact, mixed states are essential for understanding everyday phenomena,
Like what?
like why your coffee gets cold, how lasers work, or even the behavior of complex systems like the weather. We'll dive deeper into some of these fascinating applications after a short break.
Mind blown. I can't wait to learn more. We'll be right back after a short break.
Great.
Don't go anywhere.
Sounds good. Mixed states, they're all around us. They're not just a theoretical curiosity. They're essential for understanding how the universe works at a fundamental level.
So how does this connect to, say, my lukewarm coffee?
Well, it goes back to what we were discussing about decoherence.
Right.
That cup of coffee, initially in a relatively pure state with its molecules all jiggling around at a high energy level, starts interacting with the surrounding air. The air molecules bump into the coffee molecules, exchanging energy and causing the coffee state to become more mixed. Its once well-defined energy levels spread out, becoming less certain, and eventually the coffee reaches room temperature.
So my coffee cooling down isn't just about heat transfer. It's also about a transition from a more pure state to a more mixed state, due to interactions with the environment.
Fascinating. Does this apply to other systems as well?
Absolutely. It applies to everything from simple atoms to complex biological systems. It even plays a role in phenomena like the arrow of time. We experience time moving forward from order to disorder, from past to future. And this progression seems to be connected to the increasing prevalence of mixed states in the universe.
Whoa, hold on. Are you saying that our everyday experience of time might be a consequence of the universe's tendency toward mixed states? It's a deep question and one that physicists are still exploring, but there's definitely a connection. As systems interact and become more mixed, their entropy increases. Entropy is a measure of disorder, and the second law of thermodynamics tells us that entropy always increases in a closed system. So in a sense, the increasing mixedness of the universe is driving the arrow of time forward.
Okay, my brain is trying to catch up here.
Yeah.
So the universe is constantly becoming more mixed, more disordered, and this is linked to the flow of time.
Uh-huh.
But then how does entanglement fit into all of this? Remember we talked about how even entangled systems, those spooky quantum pairs linked across space, can exist in mixed states?
Right.
How does that work?
That's a great question. And it highlights a really important point about entanglement.
Okay.
Entanglement is about correlations between particles, not about knowing the exact state of each individual particle.
Could you elaborate on that?
Imagine two entangled particles, each in a mixed state.
Okay.
We don't know the exact state of either particle individually.
Right.
But we know they're correlated. If we measure one particle and find it spinning up, for example, we instantly know the other particle is spinning down, even if they're light years apart.
So the mixed state applies to the individual particles,
Yeah.
but the entanglement, the correlation between them, remains intact.
Exactly. It's like having two shuffled decks of cards, each with a random order, but with a hidden connection. If you draw a queen of hearts from one deck, you instantly know there's a queen of spades missing from the other deck, even though you don't know the exact order of cards in either deck.
That's incredible. So even in the messy world of mixed states where uncertainty reigns, there can still be this underlying order, this hidden connection between entangled particles.
Precisely. It's a reminder that even in a universe tending toward disorder, there are deep connections and underlying order that we're only beginning to understand.
This is all so mind-blowing. But before we spiral too far into the theoretical, can we bring it back down to earth with a concrete example of how mixed states and decoherence play out in the real world?
Sure. Let's think about a beam of light passing through a thick fog.
Okay.
Each photon in that beam starts in a relatively pure state, but as it travels through the fog, it interacts with the tiny water droplets getting scattered in different directions. This scattering, this interaction with the environment, causes decoherence, turning the pure state of each photon into a mixed state. The once well-defined path of the light beam becomes blurred and less predictable.
That's a great analogy. So the fog acts like the environment, introducing randomness and turning the pure light into a mixed state. And this kind of decoherence happens all the time in the real world, right?
All the time. Think about radio waves traveling through the atmosphere or electrons moving through a conductor.
Yeah.
They're constantly interacting with their environment, leading to decoherence and the formation of mixed states.
This makes me think about those poor qubits in quantum computers again. If decoherence is such a pervasive problem, how can we ever hope to build reliable quantum computers that can harness the power of these delicate quantum states?
That's the billion-dollar question. Scientists are exploring all sorts of clever strategies. One approach is to try to isolate qubits from their environment as much as possible using ultra-cold temperatures and vacuum chambers. It's like trying to create a perfectly still, silent room for those qubits to do their work undisturbed.
And what about error correction? Is that another strategy being explored?
Absolutely. Quantum error correction is a crucial area of research. It's like having a team of tiny quantum mechanics constantly monitoring the qubits and correcting any errors that pop up due to decoherence. They're like the guardians of quantum coherence, trying to keep those qubits in a pure state long enough to perform useful computations.
It sounds like a monumental challenge, but also an incredibly exciting field with so much potential. Who knows what amazing things we'll be able to do once we master the art of controlling these delicate quantum states.
Indeed. The study of pure and mixed states is at the forefront of quantum technology, with potential applications ranging from ultra-secure communications and super-fast drug discovery to material science and even artificial intelligence. It's a field that's constantly evolving, with new discoveries and breakthroughs happening all the time.
Wow, it sounds like we're on the verge of a quantum revolution. This deep dive into the world of pure and mixed states has been incredible. Can we recap the key takeaways?
We started by exploring the pristine world of pure states, where a quantum system is in a perfectly defined state with all its parts working in perfect harmony.
Yeah, we talked about how this coherence allows for those mind-boggling quantum phenomena like interference, where a single particle can seemingly be in multiple places at once.
Right, and then we ventured into the more realistic, messier realm of mixed states, where things get a bit more chaotic.
Yeah.
These states arise from decoherence, the constant interaction of a quantum system with its environment, which disrupts that pristine coherence and introduces uncertainty.
It's like the universe loves to shake things up, constantly shuffling that quantum deck of cards.
And what's fascinating is that this tendency towards mixed states, towards disorder, is actually a fundamental aspect of how the universe works. It's connected to the second law of thermodynamics, the one about entropy always increasing, and maybe even to our very perception of time moving forward.
So our lukewarm coffee, the fog blurring a beam of light, those troublesome qubits losing their coherence in quantum computers. It's all part of this grand cosmic dance towards mixed states.
Exactly. And even within this messy world of mixed states where we don't have complete knowledge of a system, there can still be hidden order, especially when entanglement comes into play.
Oh, right.
Those entangled particles, even when individually in mixed states, can maintain their spooky connection, their correlations across vast distances.
So even in the face of increasing entropy, increasing disorder, the universe still finds a way to surprise us with these subtle connections.
It's a beautiful reminder that there's always more to discover, always more to learn about the quantum world. And this understanding of pure and mixed states is not just theoretical, it has profound implications for the future of technology.
Absolutely. We talked about the challenges of building reliable quantum computers, how scientists are battling decoherence to harness the power of these delicate quantum states. And who knows what other incredible applications we'll discover as we delve deeper into this quantum realm.
It's an exciting time to be exploring these concepts. The study of pure and mixed states is at the forefront of quantum technology, with the potential to revolutionize fields like medicine, communication, material science, and even artificial intelligence.
It sounds like we're on the cusp of a quantum revolution. This has been an incredible journey into the heart of quantum mechanics. We've gone from the pristine ideal of pure states to the messy reality of mixed states, and even glimpsed the profound connections that lie beneath the surface.
Indeed. And the key takeaway is that both pure and mixed states are essential for understanding the quantum world. They're two sides of the same coin, reflecting the delicate balance between order and disorder that governs the universe.
A cosmic dance between certainty and uncertainty, between the known and the unknown. What a perfect way to sum up our exploration of these fascinating quantum states. Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.